ME347 Example 6, Laminar Boundary Layer Drag and Thickness for Uniform Flow over a Flat Plate. A flat plate with a length of 0.5 meters and width of 3 meters is immersed in a fluid stream with a velocity of 1 meter per second. The fluid stream is aligned with the length of the plate. Find the drag on one side of the plate and disturbance thickness at the end of the plate for air for part A and for water for part B at standard temperature and pressure. For part C, assuming laminar flow, discuss how the drag and disturbance thickness change if the plate is rotated 90 degrees. For this problem, we will assume steady, incompressible flow of a Newtonian fluid. Also, we assume that the flow above the plate is uniform and parallel to the plate with negligible end effects. Thus, it can be modeled as a two-dimensional boundary layer. Finally, we assume that the edges of the plate are smooth such that the boundary layer starts as laminar and will not transition to turbulent unless a critical Reynolds number of 500,000 is reached. Before we begin our calculations to find the drag and the disturbance thickness, let us calculate the Reynolds number at the end of the plate to check if the flow is still laminar. For part A, based on the properties for air at STP, the Reynolds number is about 34,000, so the boundary layer can be assumed laminar over the entire plate. Next, we use a result from the velocity solution to calculate the drag coefficient due to friction for the entire plate to be 0.007176. Finally, based on the definition of the dimensionless drag coefficient, we write the equation that can be used to calculate the friction drag. For air with a very low density, we get a very low drag of 0.00662 newtons. Next, we use another result from the velocity solution to calculate the boundary layer thickness at the end of the plate. For these conditions with air, we get 13.5 millimeters. For part B, we repeat the calculations using the properties for water at STP. For the Reynolds number, we get 490,000. This is much closer to the transition number, so we acknowledge that we are assuming that we have very clean conditions, such as a smooth plate and little free stream turbulence, for the flow to still be laminar. Based on this Reynolds number, we get a drag coefficient due to friction of 0.001897, which is a little lower than for air. Now, for water, which has a much higher density, we get a much higher drag of 1.42 newtons, which is 217 times greater than that for air. This is consistent with our experience of the difference between the force required to walk through air versus through water in a swimming pool. This also justifies using a boundary condition of zero shear stress at an air-water interface. Next, we get that the boundary layer is 3.57 millimeters. Thus, the boundary layer thickness is 3.8 times thicker for air. This is because the kinematic viscosity, which controls boundary layer growth, is higher for air than for water. To help us answer part C, let us look at plots of shear stress and disturbance thickness along the plate. As shown on the left, the boundary layer forms and grows in the x direction. Because it is theoretically of zero thickness at the leading edge, the shear stress is theoretically infinite and then drops in the x direction. In reality, the shear stress will be finite, but still at its maximum value. Thus, if the plate is rotated 90 degrees, where the length aligned with the free stream velocity increases from a half a meter to 3 meters, more of the plate will be covered with a thicker boundary layer with lower shear stresses. Thus, the friction drag will decrease significantly. Also, as implied above, the boundary layer at the end of the plate will be significantly thicker. Finally, let us look at plots of the boundary layer thickness at the end of the plate and the friction drag, which is the shear stress from the previous plot integrated over the area of the plate, versus the free stream velocity. As we can see, increasing velocity increases the drag while decreasing the thickness. Finally, We also note that in general, the boundary layer is about 3.8 times thicker for air than water, and the drag is about 220 times greater for water than air.